Welcome everybody. It's been a while, and today we'll be going over AP Physics C, waves and oscillations. So this will be a very brief introduction. It's like not a super big topic on the AP exam, but let's get to it. Alright, so we're going to talk a lot about simple harmonic motion, and this is a specific type of motion. So, you can have objects doing a lot of different things. They can be traveling different speeds, different paths. And we're going to look at a very particular type of motion where the acceleration of the object is proportional to position. And the sign, because remember acceleration is a vector, is that the acceleration moves opposite to the displacement from equilibrium. And a classic example is an object moving on a spring. So we know that for a spring we have F equals minus kx, from an earlier lesson, and we know from Newton's laws that F equals ma. And if we put in minus kx for F, we get minus kx equals ma, and the acceleration, of course, is just in the x direction. And solving for acceleration, we get a equals minus k over m times x. And over here we see that the acceleration a is proportional to position x, and the constant of proportionality is k over m, right? Because k is the spring constant, it's constant, and m is the mass, which we usually assume to be constant. So so we have a is equal to minus, and the minus sign means that we're traveling opposite to the displacement. So if x increases just slightly, the acceleration will go in the negative. It'll be negative. It'll go in the opposite direction. Cool. And I'll just copy the equations that we did over here in the top right, just so we can remember. And what we want to do now is we want to describe the motion of the object. So in the previous slide, we said that we're only going to look at this type of motion where acceleration is proportional to position. Why did we pick this? It's just because it tends to come up a lot in science and physics and math and engineering especially. So this is the type of motion that comes up a lot. So we want to study this type of motion. And now that we've made this claim, we've classified this type of motion, we're now interested in the motion of the particle. Like how exactly is it going to move when the acceleration is proportional to position? So what we'll do is we'll let omega, so this fancy symbol over here, which can draw like that, is equal to the square root of k over m. The same thing as omega squared is equal to k over m. And the reason why we do this is because we want to express this k over m, which often is, k never changes, m never changes. We want to express it as a single constant. So we'll call k over m to omega squared. Not omega, but omega squared, just because we don't have to deal with a lot of square roots, and it makes it easier. So we do that, and then we say, okay, so now acceleration, which by the way is the second derivative of position, d squared x dt squared, and that's equal to minus k over m times x. And now we're going to substitute this in, and we get the second derivative, this part here, is equal to minus omega squared x. And this is kind of like the classic equation. The second derivative of position is equal to this constant times position. And there's a whole course on this, like solving these differential equations, but we'll tell you the solution. And the solution is that x of t, and remember x is position and it's going to evolve in time, so that's why it's a function of t, is equal to a times cosine of omega t plus this new variable phi. And capital A here is also, I guess, a new variable. And this a, the omega, and the phi are all constants, and the t is time. So we can now model the position of the particle throughout time. All right, let's go over what these mean. So omega we said is square root of k over m. The amplitude is what we're going to call a. So a is the amplitude. We'll look to see why it's called that in a little bit. Phi is the phase constant. We'll come back to that too. And in general, in general, like we already defined the 3 over here, but in general, like we look at this omega t plus phi as like the phase. And this might be very new, like a new way of thinking about things, because it's we're involving trigonometry now, something that we don't really do. But bear with me here, and it'll start to make sense hopefully soon. So this is the same equation earlier, and what's often going to happen is that we're given Km, which is over here, and that helps us define what omega is, and we're given A, which is our amplitude, and we're often told to solve for phi, or we might just be told to solve for the entire equation, or we might be told to solve for like where is the particle at this point in time. So those are the types of problems that we're going to come across. Now let's take a second to try to understand what these mean. So A is the amplitude, and if you think about like trigonometric functions, what's the maximum possible value of cosine? Well, it's 1, right? So the shape of cosine, is something like this over here, where it goes between +1 and -1. And like the lowest possible value is -1, the highest possible value is 1, and cosine of 0, of course, is 1. I'm going to actually erase that just so we can see over here. So we go down here, we go back up. Okay, awesome. So cosine goes between -1 and +1. So whatever we put over here, it's just some value in between the two. And we're going to multiply this whole quantity by A. So what I'm thinking is that the maximum possible value of this expression here is just A, right? Because we're going to have A multiplied by some value between -1 and 1. And if you think about it, like if you multiply A by 0.5, it's going to shrink the value. If you multiply A by 0, it's going to make it 0. If you multiply A by minus 0.75, it's still going to go down in magnitude. But at +1 and -1, it equals exactly plus A and minus A. So that's why A is the amplitude. It kind of tells you what's the maximum possible in magnitude, what's the maximum value X will be. And now omega times t, so you can think of omega as sort of like frequency, an angular frequency. And we'll get to this bullet point in a second, but think of omega as like kind of setting the rate at how rapidly we oscillate between -1 and +1. And what I encourage you to do is plot the curves, like cosine of 10 times t and cosine of a really, really big number times t, and see what they look like, and see how one will vary a lot quicker than the other. Now this phi over here kind of tells you our offset. So if we say that at time t equals 0, the particle's at a certain position, well, what happens at time t equals 0? So I'm going to write that up over here. Say at t equals 0, we have x of 0 is equal to A times cosine of, well, the omega times t is 0, right? So we get 0 plus phi. And, if phi is equal to 0, then we have just A, because cosine of 0 is 1. But maybe we don't start off at A. Maybe our particle starts somewhere else along the curve. Maybe we start over here. Well, that's what the omega is. It's going to be our kind of like our off shift of like where are we at time t equal to 0. And that's a common question that comes up. Like maybe you're going to be told that, oh, the particle starts at 0.75. Well, then you can just if you're given A, you can just solve this equation, figure out what phi is, and substitute it back in, and that tells you that gives you like the entire range of motion. All right, cool. So now let's look at the next bullet point. So notice that the particle is at the same place each time omega t increases by 2 pi. And all this is saying is that trigonometric functions like sine and cosine, especially sine and cosine, are 2 pi periodic. So sine of x is equal to sine of 2 pi plus x. And you can think of the unit circle and, sine of theta versus sine of 2 pi, which is one revolution, I guess one circle around counterclockwise, this way, plus a little bit of more, plus another theta, and it gives you the same answer. So, so each time this omega t increases by 2 pi, then we have, we would have cosine of some like initial omega t plus v. And then if this quantity here increases by 2 pi, we would get cosine of 2 pi plus our initial omega t plus v. And these two will both be equal because we're just shifting by 2 pi. In fact, over here, you can see that t equals 2 pi over omega seconds. The particle is at the same place. And this is called a period. And the way you can see this is that let's start off at 0. So we have x of 0 is equal to a times cosine of v, right? Because the omega t is omega times 0. And if x of t equals 2 pi over omega is equal to a times cosine of omega t plus v, but we know that t, capital T, which is I guess lowercase t, is equal to 2 pi over omega. So we get this is equal to a times cosine of omega times 2 pi over omega plus v. And you can see here that the omegas cancel out. So we're just left with 2 pi plus v, and that's the same thing as just normal v. So we're at the same spot. So this capital T is called our period, and it's measured in seconds, of course, because it's a unit of time. It's like how long until you return to the same spot. And the inverse of it is called frequency, which is omega over 2 pi, the reciprocal, and it's measured in hertz. So this is different than the angular frequency. So omega is the angular frequency, but f, lowercase f, is hertz. So while omega is measured in radians per second, frequency takes out the radians from the unit, and it's scaled, so it's just in inverse seconds, per seconds, or hertz. That was a little confusing. So if there's any questions, please, I see some people in chat, please say something. I can repeat anything. I have all night for you guys. So feel free to stop me if there's any questions. I'll wait a few seconds because I think there's a delay. All right, seems like we're all good so far. Awesome. All right, next slide. All right, so we've been looking at position, right? We've been looking at x of t. So this is telling us where our particle is at a certain time. But as physicists, we care about velocity, acceleration, all these big things here. So let's take a look at velocity. So velocity is dx dt. It's the derivative of position with respect to time. And we actually have very easy job this is very easy because we're given the equation, right? We know the equation of motion is this here. I gave it to you on the first slide, right? Or I didn't give it to you, that the textbook gave it to us. The differential equations course gave it to us. So this is our equation of motion for position. Velocity is just the derivative of it. So we just take the derivative, and remember, we have a, and then the derivative of cosine is minus sine, and then we take the derivative of the inside with respect to t, of course, so we take out the omega. So we get this over here. And the acceleration is very similar. It's the derivative of velocity, right? So we do the same thing. And we're taking the derivative with respect to time. So the derivative here, remember omega would be a constant, and the sign changes to a cosine, and then we take out another omega, so we got minus omega squared. Now, any observations about this? So what I'm thinking is that, our equation of motion is this here, but our velocity is minus, so it's the opposite direction. And the acceleration is also in the opposite direction. So at a certain point, if we're traveling one way, our velocity vector is going to, like, if we're at like a positive x, our velocity is pointing in the opposite direction, and the acceleration is also pointing in the opposite direction, which is kind of makes sense. Like if you think about a spring and how it moves, and the different forces that act upon it, it'll make sense. So we're given this position here. We solved for velocity now. Now we're going to go back, and we were talking about how a is amplitude, right? So a is kind of setting our maximum position, right? So instead of cosine is between -1 and 1, now we would be between -a and a. So this would be our x of t, and this here would be t. And we would look something like this over here. And it doesn't actually have to start, it doesn't have to start at 1. It could be phase shifted a little bit. And those are supposed to be sinusoids. But yeah, exactly. Like this is what our position looks like. Now our velocity that we just solved for, what's the maximum velocity? Well, we just apply the same logic, right? We'll just say that sine has a maximum value of 1 in magnitude. So the thing that sets our maximum velocity is just the other, the coefficient, which is minus omega times a. So we have two ways actually of creating a lot of velocity. We can either extend the spring, like the object on the spring, really far, and that'll increase our a, or we can set omega. And remember, omega is equal to the square root of k over m. So we can either pick a spring with a really big spring constant, which makes sense, right? Because if you pull it as a really big spring constant, it's gonna ricochet back really fast. Or you can choose a mass that's very tiny. Like imagine attaching like a truck to a spring compared to like a tiny little paper clip. Like one of them is obviously going to travel a lot quicker. So that's what sets our velocity. And very similar to acceleration, like our cosine is, this quantity here is bounded by, plus or minus 1. And the thing that sets it is this omega squared times a. It's the same thing over here. Now, I'd like to take a second, just think about maybe there might be a problem on an AP exam, very unlikely, but maybe you'll have to design something that achieves this maximum acceleration and this much maximum velocity. So you have to kind of understand you can play with a lot of things here. Like you can play with you can play with k, m, and a, right? But then if you set k and m a certain way, then your acceleration is going to change too, because it's not omega now, but it's omega squared. So this would actually be minus k over m times a. So there's a lot of different things you can play around with here. Any questions on this? All right, cool. No questions. Okay. Now I just wrote out some hints that maybe you'll find some of these helpful. The way that I would approach these problems is we start off with a general position equation. So we'll have x of t is equal to a times cosine of stuff, where omega we define it to be the square root of k over m. And often, we don't know what k and m are, often we know what k and m are, but we don't really know what phi is, because phi is our initial position. And what we would have to do is, when we mentioned this at the beginning, is that we would solve for phi using initial condition. And all this means is that we say at x of 0, it means our position at time t equals 0 is maybe at 2, right? And our capital A, which is our amplitude, is a certain amount, like 10, and maybe our k and m are set to these values here. And the first thing we would do is we would solve for phi. So that's what I mean by initial condition. Another way is that another type of problem is maybe we don't know what K is. Like K is our spring constant. Maybe they'll make you, in part A of a problem, it'll be like, solve for K, and then part B, it would be some simple harmonic motion question. So how do you solve for K? Well, we would have to use, Newton's laws to determine our spring constant. So like maybe you're going to be given a graph where it's like, a force was applied to an object, and you're given a graph of like F and position, the force applied, and the position, and you have to use the fact that F equals minus KX, and use the slope to figure out what K is. Maybe that's a possible question for part A, and then part B is to use that K in your equation. Another thing here, acceleration is not constant. So this is not like our day one kinematics where everything was great and like acceleration's constant and we have all these equations. It's not constant, right? We just showed over here it's minus omega squared times a times this cosine here, and the cosine is going to be varying a lot, right? It'll vary between -1 and 1. So we can't use kinematics, of course. Now, amplitude is constant and is half the total distance traveled in a period. I guess maybe this is bad wording, but you just remember, like, if our graph looks like this over here, our amplitude is this here. This is our amplitude here. So if we start off here, if you look at our maximum and our minimum points, we might be at like +10, we go to -10. Our amplitude is half of that, so it would just be 10. There is a zero restoring force at equilibrium point. So there's zero restoring force at equilibrium point. So think of a spring at equilibrium, x is equal to 0, so F is equal to 0. And a few common examples, right? We have mass spring system and we have pendulum. So just have like two problems, maybe one problem where we look at a pendulum and it's exhibiting the simple harmonic motion. And sometimes we have additional force. There might be a damped harmonic system or a driven one, where we have like another external force. But I don't think I've seen this ever on an AP exam. Like, please correct me if I'm wrong, and I'll go over some questions about that. But I think that might be a little bit too much for an AP exam. Maybe we'll be getting a really hard homework, but I don't think it would be on an AP exam. All right, let's look at pendulums real quick. So all this question is going to be is that we see a pendulum in nature, and we observe that it's following simple harmonic motion, and we're going to take all the equations that we looked at today, and I kind of spoil it by giving the answer here, but we're going to look at all the stuff that we looked at today, and we're going to come up with like a way to look at like the period of motion, like how long it takes to make one circuit. So we know from Newton's laws, F equals ma, first thing we would write, and then we say that, okay, well, the force here is what? And our mass is the same, right? Acceleration is a derivative of position. And here we have to be a little bit careful because it's a pendulum, right? So we put the force as minus mg sine theta. And the video has frozen. We're having some technical difficulties. We're having some technical difficulties. I'm going to continue going until these difficulties resolve themselves. Sorry about this. All right, so we're having some technical difficulties with the camera, but let's continue. So chat, please say something if you can still see. Maybe it's just on my end. Anyway, so we were saying that we start off with F equals ma, and then we have the force is equal to minus mg sine theta. And the reason why is that the simple harmonic motion that we're observing, that some scientists has told us that, you know, I've observed this motion, let's try to quantify it, let's see if it's actually simple harmonic, is basically the shadow of this ball here. So we're observing down over here that the ball is, you know, traveling this simple harmonic motion. So this over here is like in the, like on the x-axis in one dimension. Okay, so if we're looking at this here, then our x, which is our position, is going to be, you know, with respect to this x-axis over here. It's going to be with respect to like this, if you can see over here what I'm drawing, it's going to be like this kind of motion. And, you know, we have a pendulum, so it doesn't actually travel like, it'll travel in a curve, right? It's not going to be traveling like a spring where it's completely in one dimension. It's going to be traveling, it'll have a little bit of a y component to it. So we're actually going to be observing this like arc S here. And what we want to do instead is we want to use this, we want to like, you know, consider this here, and what we're going to do is we're going to use the arc length formula, which is this S here, you know, this sector, or this little arc length on the perimeter is equal to L times theta, where theta is in radians. So if you imagine a circle here, and this here is S, say S is equal to R times theta, where R is like the radius of the circle. So we're going to use that fact, and the other thing that we're going to do is we're going to note that the force is mg times sine theta. So mg is the normal weight, right? And theta is this angle with respect to the vertical. And the sine would give us this component over here that we're interested in. It'll be, you know, opposite the angle, so it'll be kind of like the projection onto this x-axis over here. And, you know, a quick sanity check is like when the ball is like right at the bottom over here, the force will be, you know, completely the y direction, so it'll be 0. So the sine of 0 is 0, you know, at x equals 0, sine of 0 is 0, so that makes sense to me. At equilibrium, we don't have any force. All right, so I was rambling a little bit, but let's get back to, like, you know, the core of this. So we've kind of set up our parts. Now let's try to put stuff together. So F equals ma. F we said is mg times sine theta, minus actually, because it'll be opposing the direction of motion. And m is the same. Now a, which is our acceleration, is equal to which is equal to d squared s dt squared. And we're going to use the arc length formula. S is equal to L times theta, which we just said over here. And we're going to get d squared theta dt squared is equal to minus g over L times sine theta. And you can see, like, if you put in, you know, you get g over here, and the m's here cancel out. And, you know, you get g sine theta, and then you get L over here from when you substitute in. Okay, so now we're gonna, you know, we'll pause for a second here. This term on the left here is kind of like acceleration, right? The key thing is that in harmonic motion, we're interested in when acceleration is proportional to position, right? So we have here acceleration is proportional to the position here. And we can use this small angle approximation, which we'll use on the next slide. And it basically is that sine theta is approximately theta. So sine theta is approximately theta. And we basically get what we want, which is this acceleration is proportional to our position theta here. And we have a constant of proportionality, which is g over L, and similarly we're going to define it as the square root of g over L is equal to omega. So this is just like what we did earlier, where we used the square root of k over m, but this time we're going to say that our omega is the square root of this constant. So that's our new omega. And because of this, we can say that t is 2 pi over omega. And remember, everything basically applies from earlier. So once we've defined what omega is, and once you define what a is, which is our how far did we initially pull back the ball, that kind of defines our motion, because then we can just plug it into a times cosine of omega t plus phi. Yeah, and that's all there is to this one. So this is like an equation. It might be on the AP exam cheat sheet, and that's kind of how it's derived. Now we're going to look at a physical pendulum. So this is a simple pendulum, but the mass can't be treated as a point mass. This is actually like a real mass. It's a more realistic answer to the previous slide. And what we're going to do is we're going to use rotational Newton's second law. And what that is that tau is equal to I, which is our moment of inertia, times our angular velocity. Angular acceleration. So it's tau is equal to I times alpha. Now alpha, of course, is equal to d squared theta dt squared. There should be a t over there. And we know what I is. It's our moment of inertia. And t is our torque. So you can see over here we have a mass and we have a pivot over here. And we're going to, this is our center of mass here. And we're going to offset it slightly, and then we're going to observe it rock back and forth. And we're going to say that it's going to be simple harmonic motion. Well, let's take a look. So what is the torque that's being applied? Well, the torque is basically gravity, right? Because we just have this object here, and we're going to displace it slightly, and we're going to have a force that acts on the center of mass, which is equal to mg in magnitude, and it's going to be a distance d away from the pivot. And if you remember, our equation for torque is, tau is equal to, F times d times sine theta, or the same thing as F cross d. So, we have F, which is mg, and we have d, which is our distance away, and we get sine theta. So that's our torque. That's over here. And we have I, which is our moment of inertia, and we have our angular acceleration. Now we're going to do the same thing. And this thing comes a lot in physics and engineering, is that we use the small angle approximation, which says that if theta is written in radians, then sine of theta is approximately theta. And once we do that, we say that, okay, well, we just first substitute, we'll first solve for this quantity here. We get d squared theta dt squared is equal to minus, this mess over here divided by I. But instead of writing sine theta, we use the small angle approximation, and we replace that with just theta. And this over here is the same thing as minus omega squared theta, where we define omega to be the square root of mgd over I. So you'll see again, this is like a common theme, that we come up with some equation, we use some Newton's law, or we use some kind of F equals ma like thing, either rotation or translational, and we make some relationship between our gravity, angles, moment of inertia, mass, and we try to end up with this kind of equation where we have d squared x dt squared, or we have d squared theta dt squared is equal to some constant times either x or theta. And we have to make sure that this is constant, right? So m is a constant, g is a constant, d is a constant, right? Because no matter where this object is, the pivot to the center of mass is always going to be the same distance. And of course, our moment of inertia doesn't change. So these are all constants. That's why we're allowed to define this new constant, omega. So we just lump all this into omega here. And now we say this is equal to minus omega squared theta. And now we're happy because, we showed that this angular acceleration is proportional to acceleration, or is proportional to position. So angular acceleration is proportional to position with this constant of proportionality. And now once we've done here, we say, okay, everything is good. We've defined what omega is. We can define what A is. We can solve for our phase whenever we want to. And all the laws that we just derived from the first couple slides still hold. So we can still use the same differential equation. Our t, our period, is still 2 pi over omega, which is this over here. And where omega is this over here. So, just by these small little things here, we're able to derive the period of some oddly shaped mass and how it can act as a pendulum. Now there's one other type of pendulum. It's called torsion pendulum. So this occurs when there's twisting. So the twisted wire, so you can see you have a mass over here, and instead of moving this thing here and making it rock back and forth, we're going to twist it here. And this twisted wire exerts a restoring torque that's proportional to angular position. And where we won't go into an example question, but this is just more for awareness that this exists, for it to ring a bell sometime. And we use tau is equal to minus kappa times theta. And this is kind of just saying that our torque is proportional to our angular position. So if you remember, F equals ma, right? It's very similar. Torque is kind of analogous to force, and our position in terms of angle, our angular displacement is will be similar. This should be minus F equals minus kx. Is very similar to our position on a spring. So you can draw similarities between these. And tau, of course, is equal to I times alpha, right? So we can just solve these two, equate these two. So minus kappa times theta is equal to I times alpha, and alpha is the second derivative of angular position. And then solving over here for this term over here, we just get our second derivative of theta is equal to minus kappa over I times theta. And of course, kappa and I are both constants, so we can do the same thing again. We define omega is equal to the square root of kappa over I, which is our moment of inertia. And this is the equation this is our omega, and now we know omega. We can figure out what alpha A is, however we initially twist the object, and we can apply the same laws as earlier, and we can use the same laws of motion. Now the last 3 slides are just on the energy. So this is really easy actually. Kinetic energy is 1/2 mv squared, and we know what half is, we know what m is. V, you can recall this equation, this is actually v squared I wrote, but you can remember V is just omega, V is just minus omega A sine omega t plus V. Remember that? That's just taking the derivative of the position equation. Now the question is, when is this kinetic energy the greatest? Well, of course, it's when this sine quantity here is equal to 1, right? That's when we just get this coefficient. That's when we have the greatest kinetic energy. So what you would do is, if this was an AP question, you would just say, oh, well, it's when the sine quantity is equal to 1. So what does that mean? That means omega t plus phi has to equal what? It has to equal pi over 2 plus some multiple of pi, right? Because sine is, is equal to 1 over here, and it's equal to minus 1 over here. So any of these points, because we have sine squared, will give us our greatest value. So then you would just solve for t. Now potential energy is also pretty easy, because U is equal to 1/2 times kx squared, right? Because this is the potential energy of a spring, and x is just a times cosine of omega t plus v. And that's pretty much all there is to it. We just plugged it in. And when is the potential energy the greatest? Of course, it's when the cosine squared term is equal to 1. So that's just when omega t plus v is equal to 0 plus k pi. Because cosine is equal to 1 over here is equal to minus 1 over here. So at 0 and at pi. You just solve for t. And the total kinetic energy, or the total energy, is just the sum of the potential and the kinetic energies, which is just the sum of these two terms over here. So the total energy is constant over time. So k plus u, if you take these two terms here and you sum them up, you can factor out actually 1/2 k. You can factor out, and then you end up getting this over here. And you just observe here that maybe I'll write it out. Omega squared is equal to k over m. So this term here for k, you would get 1/2 times m times omega squared, which is k over m, times a squared times sine of blah blah blah, right? And of course, the m's cancel out, so you get k times a squared times sine of blah blah blah, and same thing over here, and you end up getting sine squared plus cosine squared, which is 1. So you just end up getting 1/2 k times a squared. So what this is saying is that at any point in time, your kinetic and potential energy sum up to the same amount, which makes sense because energy is conserved. So if you know the total energy and you know the kinetic energy at a particular point in time, you also know the potential energy. It's just E minus K, right? U equals E minus K. And we can also solve for V. So we can obtain the velocity at any point in time given a displacement x. And that's pretty much all that we're going to cover in today's unit. And if you have any questions, please put it in chat. I'll stick around for a little bit. And we'll see you in, I believe 2 weeks from now. That'll be the last session before next semester when we start electricity and magnetism. Thank you all for coming.